the Elmore model to model what is the delay of wire, right? I have a wire, very long. Just now I say that, let me just ignore the wire resistance, then I can get the capacitance, right? But now, no, I say, no, it's not that simple. We do have some resistance here. So what I'm going to do is this. I break it into n segments. Okay. And between all of them, I have a capacitance connect to ground. This is nothing special. You know that, right? The point is how I calculate. Well, you can again solve the differential equation and come up with an effective RC time delay. But let's just use the Elmore model, right? The first of all, right? Let's say the resistance per unit resistance per length, per unit length is small r. The capacitance per unit length is small c. Okay, so what is the total resistance? Can someone tell me? Just total resistance. We are not calculating delay. We just want to know the total resistance. What is that? If there are n segments, this is from 0. Let's start with 1, 2, 3 to n. I cut it into n segments. And the total length is L. Okay, total length is L. So what is the total resistance here? So each unit length is R, right? So the total resistance, of course, is R times L, correct? And then the total capacitance is also C times L. Is this okay? Everyone okay with this? Happy with this? Now, I cut it into N, right? Then what is the resistance here in terms of capital R? What's the resistance here? It's R divided by capital N. This is C divided by capital N. Each of them is like this, R divided by capital N, C divided by capital N. Okay, now the question is, how do I find the delay? I use Elmore's model. Like, think about this, how many capacitors I have? I have N capacitors. So I put C divided by N, C divided by N, all the way to C divided by N. I have N of them, right? And my goal is to find the delay from left to right. So I use Elmore's model. Can you tell me what is the shear capacitor resistance between from the source to the first capacitor and from the source to the final capacitor? What is the shear resistance? Anyone? It's not difficult. What is the shear resistance from here to the end and then from here to the first capacitor?
Resistance across that first node.
What is that resistance?
R, capital R by N.
Very good. R capital by N. That is the first term. Okay. Now, how about the shear resistance from the left to all the way to right and from left to the second capacitor?
2 times R by N.
2 times R by N. Very good. So you see that basically you just keep adding, right? Until the final one, it is N times R divided by N. Anyone has question? This class is very quiet. Does it make sense to you? I'm trying to use Elmore's model to divide.
Professor,
Yeah,
can you just tell how did 2R by N come once again?
yeah. So we want to find the shear capacitance, shear resistance, right? Shear resistance between two paths. There
Yes.
are two paths. One is from here to the destination that we want to calculate. Another is from here to the second capacitor. So they share two resistors,
Okay.
right? Yeah.
Yeah.
So that's why 2R divided by N.
Yeah.
Yeah.
Thank you.
So, good. Thank you. Thanks for the question. Then for the third one, it becomes free. Yeah. Now this one is just what do we call it? Geometric, not geometric. Forgot the name. What series is that? No, this is not geometric. Right. So I can take out our CN, correct? And then inside is 1 plus 2 plus 3 arithmetic series, right? Sorry, I can't think of the name now. CR divided by N squared. This one, if you forget, is 1 plus N times N divided by 2. Right? With difference can make N very large, chop into very small segment. Then this one is just equal to 1 is small, right? So N squared got canceled out. C divided by 2. Okay, so the total constant is RC, but this is the total resistance, right? Which is good. So you see that if you don't treat it as a lump, you say, oh, let me just call it this one and this one. This is RC, which is wrong. Indeed, right, it is compared to simple lump, is only half of the delay, RC divided by 2. That's the first thing. Second thing is, as a designer, you don't care the absolute length, right? Or you care, but as a technology, you care about the capacitance and resistance per unit length. I just say that the capacitance is small C times L, and then small R times L for the resistance, right? It's just CR L squared divided by 2. Right, so this one for this one. And what does it mean? What does it mean? It means for the same technology, if you increase your wire by 2 times, you increase the delay by 4 times. It's a quadratic increase. That's why you don't want to have a very long wire for the same technology. If you can cut it by half, actually reduce it by 1/4 of the delay. That is a big deal, right? In the past, maybe not that important because your logic gate has more delay. But now the wire has big delay. You need to think of this very carefully. Okay? So just like here, just repeat what I said. If you treat it as a lump, it is only 6.9 RC, right? But now this one with this time constant, let me just put time constant. I don't, because later you will see something. Time constant RC now is RC divided by 2. It's shorter, right? So by taking the lump into account, it is easier. It looks better. But remember, the most important thing is it go up quadratically with your wire length. So you're paying a lot by, if you are lazy, try to say, let me just connect this wire to that gate. Then maybe that is not a good idea. Right? Computer can simulate for you, but this type of insight is very important when you design it, because computer can never find the global optimum, in my opinion. So you need to start with something good instead of asking synopsis tool or cadence tool to optimize for you. They will, but they cannot get you out from some very bad local maximum. Okay. Any questions? Now, if no, this is a summary, but no worry about this. I'm not asking to know this, but to memorize this, right? All this equation, just to let you know that actually the real solution is very complicated. But I want you to pay attention to this one, 0 to 50% delay, which is related to your delay that we're calculating. If you use the lump circuit, it's 0.69 RC, okay? But if you use not the lump distributed one, it's 0.38. Okay, this is different from Elmore. Elmore is talking about this one divided by 2 will be 0.345, right? But Elmore by itself is an approximation. Here, what I'm giving you is the real one. Okay, so we are going to use 0.38 in the calculation when you don't need to do any derivation. Okay. Another problem of this is that it's not just delay, right? Here is showing the delay. This is a wire from X to L. I apply a pulse like this, a step pulse. Yeah, it does take about 0.6 nanosecond to reach here. Right? You wait for 0.0 nanosecond later, 0.6 nanosecond later, eventually the signal reach the end of the wire. That is the delay of your gate, right? So you cannot have a clock frequency faster than that. Otherwise, you cannot capture the signal. But not just that, it also gets distorted. If you look at the waveform here, this is very sharp. When you come to here, it becomes this. When you come to here, it becomes this. And eventually, it becomes this. So your it's just like a diffusion equation, okay? It keep diffuse out. It cannot keep the pulse that it has. Right? So this is another problem. It means, or on the other hand, you can say the rise time will increase. Okay. Now, then we want to look at another case. Right now, I want to drive a RC9. Do you see that when you see a figure like this, just like what I said before, the first thing is you have to think, what are you talking about, Professor? Do I really apply a pulse and then a resistor like what we do in our undergraduate lab to understand the RC delay? No, right? We are talking about a chip. What really inside is, I have a inverter, for example. And this is going from 1 to 0. I turn this off. This is driving a line, transmission line. This is transmission line, very long line, right? It has R, it has C, it has L, and it is going here. The effective resistance is Rs. What is Rs? Rs is what we calculate, what we just discussed in the what did we learn last lecture, right? The resistance, effective resistance of your gate. How do we calculate this one? Right? So then it depends, right? If we assume two cases, if we are lazy, or if our W is very small, let's say our W is small, we can just use the lump model, right? So basically what I have is just Rs and then a capacitor, which is CW times L times CL. So I was wrong. Actually, this L is not inductance, it's just the length, okay? Just the length of the wire. Right? So what is the delay for this one if it is lump model? Can someone remind me? We just discussed. Or the time constant. What is the time constant of this model?
0.69 RC.
Say again, you say too fast.
0.69 RC.
Very good. Now, I only asked for time constant, so let's don't put 0.69 first. And you say RC, you mean RS times C CWL, right?
Yes, sir.
Right. Okay, that is good. But at the same time, right, when RW is not small, there has additional delay, right, due within the wire. And that has a time constant of what? RW CWL squared divided by 2, just within this line, right? So that's how we separate it. Well, you see, if you want to solve this whole equation, it's very complicated. But now we see it in this way. We have an RS. This RS is just driving a capacitor. So then we have this one. And then within this line, it's a lump. Then it has its delay constant like this. Okay, so the total delay is going to be, like what you just said, 0.69 RSCWL plus 0.38 RWCWL squared divided by 2. Why 0.38? I just told you 0.38 is for the lump part and 0.69 is for the RC part. Let's stop for 1 minute, pause for 1 minute, make sure you are all okay with this. Are these clear? So here show a concept. To find the delay, you find the time constant, right? Time constant, you can use RC. If it is lump, it's RC divided by 2. Okay, if it is okay, let's move forward, right? So there's a rule of thumb, right? How do we design? How do we do the calculation, right? As I mentioned many times, propagation delay of lump RC is 0.69 RC, right? Memorize this, nothing, not hurting you, right? It's electrical engineer. For distributor one is 0.38 RC, but time constant is 0.5 RC, right? This is by Elmore's model. This is Elmore's model, right? Okay, 6.9 and 3.8. Now, do I need to consider them? First of all, you only consider RC delay if the RC delay is longer than your gate time. If your gate is so fast, then you consider it, right? What is the delay of the RC? It is 0.38 RCL squared, right? And what is the delay of a gate? The gate is due to the RS, but here we don't say that, we just put the gate, right? You rearrange it. It means that you need to have the wire larger than this one in order to make sense to consider the delay. Okay, if your wire is very short, then don't add this component. It makes your calculation more troublesome. But again, nowadays, it's not about calculation. It's that your insight. Someone present you the figure, the delay, right? You got a lot of simulation. You know what's going on, but you don't understand why. Then you start break into different components. Then you say, okay, maybe now I can ignore this RC delay because this is much shorter than this one. So I don't need to consider the delay due to the wire. I only need to consider the delay due to the gate. And one more thing is, you only consider if your rise time is much smaller than RC, right? If your gate takes so much time, your signal takes so much time, let's say 1 nanosecond. Let's say you have some very bad circuit, 1 nanosecond. And then the delay is only, RC delay is only 1 picosecond. Why do you want to consider the delay? Because the rise time already gated how fast you can switch, right? So only when our rise time is smaller than the RC, will you consider the delay? Do you get it? Understand? Okay, so just a rule of thumb, right?